So hello everyone, this is lecture 23 for the solid state physics, and see what I have here. This Saturn, you can also spot the Titan inside. This was gifted and I am loving this. So let's continue. In the last lecture we discussed what? The free electron theory and the specific heat. We saw all this, and the mathematical form we proved that how electronic specific heat depends on temperature mathematically and quantitatively. We already discussed this. So there is some, and also the Fermi energy and Fermi velocity, all the Fermi momentum and all, we discussed the formulas and the Fermi radius and all. So there are some questions based on that, so try to solve them. In the next lecture I will provide the solutions otherwise. Okay, so these are the questions. Sodium is BCC structure with atomic radius is given 1.86 angstrom. Calculate the following, that is number density, then our Fermi energy at the 0 Kelvin, average energy, then E rho, Kf, Pf, Vf, Tf at T equal to 0 Kelvin. Everything you know what is this. This is energy density and Fermi radius and all. Then find the specific heat, electron specific heat at T equal to 100 Kelvin and 200 Kelvin. Same question do for A equal to 3.6 angstrom. Okay, if A is given, that is our lattice constant. If it is given, then solve this. Then there is one more question, find Fermi energy, average energy, energy density, and these all factors for non-relativistic free electron in 1D and 2D. So use a dispersion relation we discussed before and try to solve. Then there is one more question for relativistic electron, solve these terms. Then prove that the Fermi pressure for non-relativistic electron, Fermi pressure as we discussed that here it is as electron gas. So Fermi pressure for non-relativistic electron in 3D is this 2 by 5 and EF naught. Prove this. You need to prove this. Where P is nothing but del E by del V. So you can solve this from the energy equation and just differentiate it with respect to volume. Okay, and one more part we have, prove that the bulk modulus B equal to 2 by 3 and EF naught. Use this formula, B equal to minus dP over del V upon V. This is nothing but pressure and this is volumetric strain, and we can write it like this. Try to solve these questions. If you are having any doubts, then we will see that in the next lecture. Now today's topic is Drude model, DRUDE, Drude model of electrical conductivity. We will see some things. Okay, so when there was nothing and first we have only one tool to find the conductivity and all, that was Ohm's law. In the previous era, Ohm's era. So we have only this thing, and what we did, we have a conductor here and we put a battery and a meter. Then what we did, we just changed the voltage and measure the current and take the readings and put it in the graph, and then we see that the slope will give us the 1 upon r, and that's how we can find the resistance. And we observe these by putting different type of resistance and changing its dimensions. Then we find that resistance is directly proportional to length, inversely proportional to area, and here area is nothing but, if we see it is D, it is W, then area will be dW, that is cross section area. This is length L. Then we can write if this equation is there, then proportionality constant introduced, that is rho, and rho is nothing but the resistivity, R equal to rho L by A. So this was the formula from the Ohm's law, and from here we can see that this rho is nothing but resistivity, and 1 upon rho will give us conductivity. Okay, wait just a minute. Now Ohm's law can also be written in this form, that is J equal to sigma E, and here J is current density, sigma is conductivity, and E is electric field. And how we can prove this, we can write it like this, just to see. J is I by A, current per unit area, current density, and electric field is nothing but potential divided by length, and from here we can see that sigma is nothing but 1 upon rho. Rho will came this side and length came this side, and V upon I, and we know this is resistance, and resistance is nothing but rho L by A. So we came to this equation from this equation. So that's why we can write Ohm's law in this way also. So this was the things initially. Then came the Drude model, means there was a different approach to calculate the conductivity, resistivity and all. So we'll see that, okay, how these things happen. So what they assume that, not assume, actually this happened, or what was the theory? It was actually a theoretical thing. So let's say we have a conductor here, and we put a battery and put a ammeter here. Then we will see that electron inside this conductor will face a or feel a force from this potential, because this potential difference will give a electric field inside this conductor, and this electron gonna feel a force which will pull it, and that force will move them, and that will give the current in the circuit. Okay, so how can we denote this force? We write it as Fe, that is nothing but Q, that is charge into electric field, and charge is nothing but minus E, electron. So electric force due to potential difference is nothing but this. We call this force as electric force due to potential difference. Then we know that anything moving, then in the real world they gonna face dissipative forces, and dissipative forces can be anything, the viscous force, frictional force and anything. But here in the case of conductor, then we see that in this crystal or conductor, when the electrons move, they will see that there will be impurities in this structure or the crystal, and those impurities will cause the resistance to this moving from them, means stop moving from them, stop moving these electrons. And the resistance will came also from the phonons inside. Okay, phonons are nothing but the modes of vibrations, and the impurities inside the crystal. So though both will cause the friction in the conductor, they will try to stop the movement of electrons. Okay, so we will have also a frictional force inside, and electric force which is make them move, and the force which is stopping them. So what will the frictional force? That will be minus. And how we calculate this? We take the proportionality things, means we know that heavier the mass, the heavier will be the friction. So that's why the proportionality, and more the velocity, more will the friction, and small the time, the collision time, there will be more friction when there is a very small collision time. Okay, means you can see that if in a gas, then if you increase the temperature, then we see that when the collision time decreases, means many more collisions taking place at a very small time, then the resistance increases. We see that in the conductor case, the temperature with temperature resistivity increases. So that's why we can say that tau decreases. So means it is inversely proportional to tau, that is the frictional force. So we'll see that net force is the sum of these forces on the electron inside this conductor, and here it is collision time, and negative sign shows that frictional force is opposite to V, means it is opposite to velocity. Where it is moving, it is opposite to the velocity, means electrons are moving this side, then force will be this side. And then let's say if there is electron first it moves from here to here and traveled lambda 1 distance without any collision, then it traveled from here to here with lambda 2, then this distance lambda 2 again, lambda 3, then it can be anything, lambda 4, lambda 5, lambda 5 again, anything. So we see that these are free paths, means without collision the path traveled is called free path. And when you take the average of all these distances, lambda 1, lambda 2, lambda 3, and divide by the total number of collisions, then you will get the mean free path. This is called the mean free path lambda. And likewise, if the time taken from in the one collision is tau 1, in 2 is it tau 2, in 3 is tau 3, then average of all these collision times will give us mean collision time. In the coming section we will see that relaxation time and mean collision time are same. So we'll see that. So hope it is clear up to here. Let's move. So V equal to lambda by tau, Means we know that we can define this. If electrons are moving with very high velocity or anything that is v velocity here, then v is nothing but distance, that is lambda, and time lambda by tau. So we can write it here, and lambda can be written as v tau. Okay, so if electrons are near Fermi level, so you guys are aware about the Fermi level because we already discussed this. The energy means the electrons which are having energy and nearby Fermi level, then we call the velocity of those electrons as Fermi velocity. We calculated, means here I gave you the questions, you will see the Fermi velocity for different type of sodium, aluminium and different type of elements. So the average of all these velocity and when we calculate the collision time, it came out approximately, we can write it like this, 10 to the minus 14 seconds. Okay, just to keep these numbers in mind, they can be helpful in the exams. So now we can say that total force on electrons are nothing but F, electric force due to the potential, and the frictional force. And we already write the terms, so we can write just a formula, minus E, capital E, minus mv over divided by tau. So here force is nothing but m dv upon dt, that is our acceleration. Okay, so this and this. Now we can let me show you one thing. This is a bracket, not a graph. So let's say we have earth here and a particle is dropping from very high height, and initial velocity is 0. So what you see that velocity should increase because of gravitational force, means a constant force mg is applying on the object. Then when there is constant force, then there is a constant acceleration also, and acceleration leads to increase in speed. But when we plot this increase in speed with respect to time, then we see that this type of curve we get, means initially the speed is increasing with time, then it came to saturation, it become constant. So this is the actual values what we see in the world, real world. So what happened inside, means how this becomes constant and there is no acceleration after a particular time. So this velocity actually called the terminal velocity, means as water droplets or the rain droplets drops, they become constant, their speed become constant after a particular time. So how it happened, means when something is moving inside the environment, then it gonna face the dissipative forces or friction forces. So let's say they will be in a positive direction. So as speed is increasing, so we know that friction force is directly proportional to speed, so this also increasing. So at a particular point, time comes when these both forces becomes equal, and net force on the particle becomes 0, then acceleration will also be 0. So at that time the velocity saturates, and we call that terminal velocity. Okay, so likewise inside a conductor also, after a particular time both forces becomes equal, both forces, means inside this conductor there is friction force and the electric force becomes equal, then they gives a steady velocity inside a conductor, and we call that drift velocity. So we will change here all the v expression as vd, then this term will become 0 because vd is constant and it is a steady state condition. So in steady state condition v is constant, and we call that v as drift velocity vd. So m dvd upon this minus e mvd upon tau, this becomes 0, and from here we can find the drift velocity, that will be minus e tau e upon m. So you get the drift velocity expression. Now we can find the conductivity and all, conductivity, resistivity from this, because this is a Drude model. So we will see that how we find this from here. So how we define the current density, that is nothing but minus n e vd. So how we write this expression, this n is nothing but number density, number of electrons per unit volume, e is electron, and vd is speed. So if you see the units of this, it is L upon T, and it is nothing but number divided by volume. So volume and length above, meter cube meter will cancel out, meter square gives in the denominator, and number will give you total number of charge, and dt. So total number charge divided by dt, that will give you current, per unit meter square, means per unit area. So current per unit area will give you J. That's how we get this expression for the current density. Now just substitute the value of Vd here, E tau E by M. So you will get minus, then it will cancel out. And now we know the expression from the Ohm's law, J equal to sigma E. Okay, so now we compare this with this. So from here you can see the conductivity is nothing but this, Ne square tau divided by M. This is conductivity. And for resistivity, just the reciprocal, rho will be 1 upon sigma, that will be M upon Ne square tau. So this expression is for the resistivity. So we find the resistivity and conductivity from the Drude model. Okay. Now let's discuss the relaxation time. I told you that I will prove that both are equal, the collision time. So let's see them. So let's assume we have this circuit, and in this conductor we will see that electrons are moving. And just imagine a case that after a particular time we open this circuit. Means there is no electric field inside this circuit. Then what happens? When there is no current and no electric field, no potential? Then the electrons inside will again start to, means they will try to come relax, means they will come to the steady state, means their velocity start to decrease in particular. Okay, so how this happens, let's see from the equations. We have these equations, this one. So now Vd is not constant, it is decreasing, and so we'll use this expression actually, because it's now not Vd, because it's not a steady state. Now there is no voltage in the circuit, so it will be decreasing. So M dV divided by dt. So electric field is 0 because we have opened the circuit. So what the equation this becomes? This will be like this: M dVd divided by dt, 0 minus M Vd divided by tau. Now just we need to separate the variables and do the integration. Vd came this side and M will cancel out, 1 upon tau dt. So this will give you log Vd, and here it came the T by tau plus C. Now we can find this constant. There is something constant, integration constant. When T equal to 0, what happens? C will be ln Vd naught. Okay, so we get the value of C, just substitute it here, and we'll get the expression as, and there will be ln Vd naught, it became in minus, and Vd divided by Vd naught. So we get this expression. From here we can write it as this equal to exponential e to the power minus t upon tau. Then Vd naught becomes here, goes here, and now we can see that drift velocity at particular any time t will be written as this Vdt at Vd naught e to the power minus t upon tau. So this equation gives us the way velocity will decrease after removing the electric field. So you can see here, means this velocity is going to decrease with time. So when you place the t infinity here, means at very large time, so what you will see that e to the minus infinity will give you infinity in the denominator, and this term will becomes 0. Means this value becomes 0 only at infinity. So that's why when we plot these, we never get the 0, because we can't plot the infinity on the plot. So you can see if we plot Vdt and with time, so we see that Vdt start to decrease with time exponentially, and exponential terms never becomes 0, means only at infinity they becomes 0. Okay, so what happen when t equal to tau? Then we will see that Vdt will becomes 1 by exponential Vd naught, means it will be e to the minus 1, it will come out to be in the divide. Then Vdt will be Vd naught divided by E at t equal to tau. So what we see that exponential terms never touches this axis, because only at infinity they can become 0. So what we assume that when the value of this term came out to be 1 upon exponential type of 1 upon exponential of this value, then we assume it as 0. Means after that it is not valuable, means we neglect all the things and we assume that now it doesn't matter to us. after this value. Means when this speed becomes 1 upon exponential time this value, then we have no use of this. After this we assume it's 0 here. Okay, so that's how you can calculate. Means now this is happening only when t equal to tau, and tau is nothing but mean collision time. So and this much time is taken by the electron to relax here. Okay, so we call this as relaxation time also. So that's why the relaxation time tau and the mean collision time tau both are same. Okay, so I hope you get the thing what I was trying to convey. Okay, and then again thank you everyone for listening the lecture and share it. So thank you again, bye bye.